Okay, so we're going to talk a little bit more about the possible covalent bonds that are out there and why they're so important to life. So who can form covalent bonds? Well, one of the things that let's talk about who doesn't. Metals do not form covalent bonds. The only exceptions to that are very rarely lithium and beryllium, but basically the rule of thumb with this is metals, no covalent bonds. Metals are going to form ionic bonds. Only nonmetals and metalloids can form covalent bonds. Now, the electron configuration is really important. Where the electrons are located are important to what kinds of bonds they're going to form. Carbon has 4 unpaired electrons, which basically means that it can form 4 bonds. And those 4 bonds are going to go in 4 directions in space. Now, 4 directions in 3-dimensional space ends up making a shape that's similar to this. We'll talk more about what molecular geometry is and how that applies. Nitrogen has a lone pair and then 3 unpaired electrons. That lone pair takes up space, and so that lone pair you could think of as being right up here, and so it's going to have the same shape that the carbon is going to have, except that instead of having a bond in that one direction, it has a lone pair. Oxygen has 2 lone pairs and 2 unpaired electrons, so oxygen's able to make 2 bonds. And so it's going to take on the same shape that the carbon and nitrogen did, with the exception being that you're going to have these 2 lone pairs sticking up where there were bonds. And again, just a definition, lone pairs are defined as the pair of electrons that are not involved in chemical bonding. They still occupy space where bonds would have been had they been unpaired and could have created a bonding pair. All right. Why do electrons fill orbitals one at a time before they pair up? Well, it's because electrons repel each other, and they want to be as far apart from each other as possible. This also happens with chemical bonds. The bonding pairs and the lone pairs want to be as far away from each other as they can be because of that electron repulsion, which is why, even though you may draw your carbon on a piece of paper looking something like a T with a 90-degree angle, in reality it spreads out at 109 degrees like in this shape, because those electrons are trying to spread out in 3-dimensional space. Now, there is an exception to the octet rule, and that is boron, because boron only has 3 unpaired electrons. And so they're going to spread out in space to be at 120-degree angles, like this, and form this kind of Y-shaped pattern. And if you don't have at least 4 valence electrons, you are not going to be able to follow the octet rule. But those 3 unpaired electrons can make 3 bonds. Okay, so let's kind of look at some examples of what these bonds end up looking like. So here is a molecule called ethane. It's C2H8, and you've got all single bonds. So each carbon is spreading out in 3 dimensions. You've got a single bond between the carbons, and then these 3 carbon-hydrogen bonds are spreading out. Same with this molecule. And you've got a 3-dimensional shape to it. However, when you begin to have multiple bonds, when you have multiple bonding pairs, the shape will begin to flatten. And for every double bond you make, you remove a dimension in space. So everything with single bonds is going to be 3-dimensional. However, if you have double bonds, you've lost a dimension. You've used up one of the electrons that could be sticking out in space, and you've added it to the plane. And so a double bond like ethene, which is C2H6, ends up creating this flat shape like this, or what we call a 2-dimensional plane. And this rotating image shows you what that plane looks like. If we were to add a triple bond, we've removed yet another dimension in space, because we've lost another unpaired electron. And so, in the case of a triple bond, since we've lost 2 dimensions, we go from 3 to 2 to 1 dimension. 1 dimension is a line. So these are what we call linear molecules. So whenever you have a triple bond, that is going to make a linear molecule. All right, so if carbon has 4 unpaired electrons, what happens if you can make a single and a triple? You could make 2, if I can do my Vulcan symbol, 2 doubles. You could make 4 singles. You could make a double and 2 singles. What about a quadruple bond? Could you have 4 bonds together? Here's an example of 2 double bonds. Now again, you lose 1 dimension for each double bond. So we've lost 1 dimension here, so we've gone from 3 to 2, and then we've lost another dimension here, which takes us from 2 to 1, and you'll notice that carbon dioxide is a linear molecule. It goes in a line. Quadruple bonds? Sorry, not possible. The reason is that once you create a linear shape like this, then those unpaired electrons that are sticking off the ends cannot come all the way around and meet each other in the middle. They can't bend around. So they can form single bonds off on the ends, but they are not able to make a quadruple bond. So that is not a choice. You can have single bonds, you can have double bonds, you can have triple bonds, but you can't have quadruple bonds. Carbon is a particularly important atom because it can make 4 different bonds and a number of different combinations. I've kind of gone over them. 4 singles, a double and 2 singles. You can make 2 doubles. You could make a triple and a single. So there's a number of different combinations. And thus, that allows carbon to make different shapes and dimensions throughout these different molecules that it can make. Again, carbon, 4 unpaired electrons, 4 bonds. Nitrogen, 3 unpaired electrons, 3 bonds. Oxygen, 2 unpaired electrons, 2 bonds. In fact, there's a rule that says you can never make more bonds than the number of unpaired electrons that you have. So here are a number of different combinations that oxygen and hydrogen and carbon can make. And you can see these different shapes that can form because of the flexibility that having 4 bonds allows carbon to have. Carbon, in fact, is the key to life. It is the backbone of life because of all the combinations of different shapes. In fact, carbons can wrap around on themselves and form various rings of pentagons and hexagons and so forth. So you can get all these different shapes and varieties of structures. So that is why all the most important molecules of life, everything from glucose and proteins and hormones and all these molecules are made of carbon atoms. In fact, DNA is based on a backbone of carbon, with a number of other atoms that can make multiple bonds, like nitrogen and oxygen and sulfur. DNA contains the genetic code, the building blocks of life. In fact, the largest molecules known in the universe are proteins in biological organisms, where you can have thousands, if not millions, of atoms in one gigantic molecule, with incredible shapes that can wrap around and form all over each other, shapes that can open up to absorb certain types of molecules that are needed, and then close up and seal them in, and then open up again. They've got incredible flexibility due to the number of bonds that carbon can make.